Nice to see so many of you. Nice to see that the plague hasn't caught anybody. I guess we mustn't even joke about those things. It's just nice to see the class so full of people. Guys, today we're going to be doing acids and bases. Now, there's two ways we can do it. I'm going to ask if it's okay with Ms. Drayden, and if it's okay with one of you to bring your desk and come and sit right by the computer. You see, I like to teach asking questions, and I need that person to tell me what you're saying. But then you're going to be the star of a YouTube video. So if any of you are prepared to do that, bring your desk and chair and come sit right by the computer, so then you can relay to me what other people are saying. You'll be like a relay or telegraph station. Otherwise, I'm just going to lecture, and then it's going to be a little bit more boring. Okay. Oh. Well done. At least the top half of you will be the star of a video. Okay, I didn't even get to see who it is.
It's me, sir. It's Matthew.
Matthew, thank you so much, Matthew. Yeah, everyone looks like we all dressed for the Arctic weather these days, which is fantastic. I'm dressed with I've got a cup of tea, I've got a hot water bottle, I've got everything here to keep me warm. I just don't know if I've got a piece of chalk. Okay, we're going to have some talk and chalk. So today we're going to be doing acids and bases. Okay, now when you learnt about elements, that is like learning the alphabet. Can you tell me some of the elements that you know and their valency? So Matthew, maybe you could ask them if they know any elements and their valency. Say, what's this element? Okay, so do you see the element? It's got a valency of?
Sir, we can't see.
You can't see?
Yes, sir. It's too high up for us.
It's my apologies. Can you see now?
Not everyone can see it, sir.
Okay. What don't you see? Can you not see that high?
Okay. I can see so.
So we say that those elements are like our alphabet in chemistry. So hydrogen's got a valency of 1. Oxygen's got a valency of 2. Carbon's got a valency of 4. Sodium has got a valency of 1. Potassium's got a valency of 1. Lithium's got a valency of 1. Calcium's got a valency of 2, etc. So that is like our alphabet. But now we join our alphabet into words. So now we must begin to recognize substances like SO4, NO3, PO3. Let's think of a few. PO4. Now, we call those words compounds. Matthew, can everyone see that?
Yes, sir, I can.
Great. Now, just like the letters have valency, that means I've drawn them by little bonds or hooks. Do you guys recognize these patterns? Do you begin to recognize those patterns? They're common patterns. They're like the words of chemistry. But they too have a valency. Does anyone know how many hooks SO4 has got? Anyone?
Just say your answer.
SO4, how many hooks has it got?
4, sir.
4, they say. Okay. Let them guess again. It's not 4. I'll give you a hint. It's 2 minus. So how many hooks has it got?
2, sir.
2. Okay. That, and anyone know what the name of that SO4 is called?
Sulfuric acid. No, not sulfuric acid. Sulfur. Sulfur oxide, sir.
That is quite funny. Okay. But thank you, guys. I'm appreciating your interaction. No, it's called sulfate. So you see, when we first learn to read, we learn C, we say ka, a, t, and then we learn to say cat. Now we say S and O and 4 and whatever, and then we learn that it's sulfate. Okay, anyone know how many hooks that has got?
CO3. So is that CO3 or CO2?
CO3.
CO3. So is it 1?
Okay. CO3 2 minus. Any more guesses? You've already tried, I think, 3 or whatever.
2, sir.
2. Well done. Okay. Anyone know what its name is?
Is it carbonate, sir?
Matthew, you're a genius, or whoever's helping you.
Oh.
Okay, anyone know how many hooks this one has got?
What is it?
PO4. NO3 or PO4, sir?
Nh3.
The NO3.
2, sir.
There's the hint.
1, sir.
Great. Okay, so that's got 1 hook. And last of all, anyone know how many that's got? I think I should give my next salary if anyone gets that one correct.
1, sir.
Okay. No.
Is that 3, sir?
There we go. So no one gets my next salary. You wouldn't miss it much. It's very small. Anyone know what this is called? This PO4?
Phosphate, sir.
Well done. And anyone know what this top one is called?
Nitrate.
Nitrate. Lovely. Okay, so if I could just give a hint, go and brush up on the names of all, these are called anions. Go and brush up on their names and their valency, because many people think that they can get through grade 10, grade 11, and grade 12 without knowing the names and valency of these things. And to tell the truth, maybe they can, but it's really going to be like emerging from school illiterate. Okay, so learn those names. Now, if we take those same things and we combine them with H, wherever we see, it's unjoined. Then we have what? Anyone know what we've got? So this one would be H2SO4. This one would be H2CO3. This one would be H3PO4. And this and that one, sorry, would be HNO3. Anyone know what those things are?
It's acid.
Well done. So those are all acids. Take almost any anion. Let me give you another anion. Here's an anion, chlorine minus. Attach it to hydrogen. Who could tell me what that acid is going to be?
HCl.
Anyone know its name?
Hydrochloric acid, sir.
Lovely. Hydrochloric acid. Okay, let's just see if you know what is the name of this acid.
Which acid, sir? Sulfuric acid, sir.
Sulfuric acid. So what do? You take sulf, eat the 8. Okay, get rid of the 8. You scratch out the 8 and you go sulfuric acid. Uric, or you have a ric at the end of it. A ric normally. Look at this, hydrochloric acid. Okay, this one would be, take the nitrate and turn that into
Nitric acid.
nitric. Nitrate becomes nitric acid. And this one doesn't quite follow that rule, but it's, anyone know what H2CO3 is? I guess I could venture half my salary that you wouldn't know that one.
Carbonic acid.
Right, I'm glad I didn't venture it, but you're right, carbonic. And that would be phosphoric acid. Okay, so phosphoric. There's the ric. Phosphate, phoric. Nitrate, nitric. Carbonic, well, carbonate becomes carbonic. Okay, So there are some of the acids. But guys, what I have to have you do is when you see that and that, I need you to know that they're going to, when you put them in water, they're going to fall apart. Your words are going to disintegrate into what do they call parts of a word? My English fails me for the moment. What do you call a part of a word? Yeah, I've forgotten. Anyway, like you get catalyst.
Syllables.
Thank you. Okay, this is going to disintegrate into syllables. Okay, I failed English. Now, where is it going to disintegrate? In the same place where it joined the hydrogen. So I need you guys to be able to know that when you put that in water, it's going to crack there. That's 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 going to crack there. And so let's be ready for it. When it cracks, let's be ready to know where it's going to fall apart. We added the hydrogens to these ions, and they're going to fall apart when we put them in water. Okay. Now, this is how I think of it. And I'm not quite sure if this is politically correct or gender correct or anything. But I always think of this as like a marriage where hydrogen is married to sulfate. Sulfate you can think of as a gaggle of gals. Hydrogen is two guys. So two guys are married to this group of gals. Three guys are married to the phosphate. One is married to one. That's a monogamous marriage. Two are married to that one. So that is called a polyandrous marriage. One is married to one. That's a monogamous marriage. Okay, so they married. But you know, in chemistry, there's no faithfulness. They're just partners. They're just there for the good times. And then when the times become tough or when something comes along that's better, they all just disintegrate and go with other partners. So let's not call it a marriage. Let's call it they are partners with each other. Okay. So now I'm going to add water to them. Okay, let me get rid of this. Okay, let's start with a nice simple one like HCl plus water. Now, when you add water to this side is slightly positive, this side is slightly negative, and water is like a big magnet. And water will start to pull it apart. So water's got a positive side and a negative side. I'm not going to draw it, but all the negatives align to the hydrogen side and all the positives align to the chlorine side. And then we say that, anyone know what we call it when water surrounds and dissolves something? Anyone know a fancy word for that? Anyone? Okay, we say it's hydrated. And then this will dissociate or ionize and fall apart. And then we're going to get this H3O plus Cl minus. And what can we say about that? Well, let's get rid of the stuff that's distracting. We say that that has donated a hydrogen. So now this happy little marriage falls apart. Hydrogen was dating chlorine, along comes water, and lots of waters pull on them. There's social interaction, and these two who've been together fall apart, and the chlorine goes off, and the water combines with the hydrogen, and it forms that. Okay, did one of these on the left donate a hydrogen? Did one donate a hydrogen?
Yes, sir.
And which one?
The hydrochloric acid.
The hydrochloric acid. And it became that. So according to Bronsted-Lowry, an acid is not just a hydrogen donator, but a proton donor. So this one is an acid. And once it's donated the hydrogen, it becomes chlorine minus. Now the water gains the hydrogen and it becomes H3O plus. So this is going to form that. This one is going to form that. So Bronsted-Lowry says an acid is a proton donor. But why is it a proton? Didn't it just donate a hydrogen? Does anyone know why we say it's a proton that it gave, not a hydrogen? Anyone got some explanation for that? Look, what is a hydrogen? It's just one positive and one negative. And the positive went across to there, but it left its negative behind on the chlorine. So the hydrogen without its negative is called a proton. So hydrogen is just a proton and an electron. So this is what chlorine says to hydrogen. Hey, we've been dating for a long time. I don't care if you leave, but just leave your E-bucks behind. So what does chlorine do? It's left with its electron, with hydrogen's electron. Yeah, you can go, you unfaithful scallywag. But just leave your electron behind. So there's hydrogen's electron, and now hydrogen has gone off with water. So now what Bronsted-Lowry says is whatever gains the proton is called a base. A base is a proton gainer. What gained the proton? Water. So water accepted the proton and became this ion here. Matthew, does anyone know what the H3O plus ion is called?
These are hydronium ions.
Well done. Who said that?
The whole class.
The whole class. Well done. Either I've taught very well or you're all geniuses. That's well done. Okay, so we're going to talk about the hydronium ion. So Bronsted-Lowry says that anything that gains a proton is a base. Do you see why water's a base? But now look at this. If we reverse the reaction, and that goes to form that goes to form that, what is that acting as? Look what it does. H3O plus will go to form H2O. It will lose a proton to go to form that. So if it loses a proton, what is that?
It's an acid.
I heard you say so. That is now become an acid. And chlorine can gain a chlorine can gain a hydrogen from here. And if it gains a hydrogen, it's called a base. So according to Bronsted-Lowry, an acid is a proton donor. A base is a proton acceptor. And I hope you can see that chlorine accepts that and goes back to form that. So chlorine is a base. Cl minus is a base, chlorine ion. Now, Matthew and the class, have you ever thought of that as a base or that as a base? Have you ever thought that water is a base? And that chlorine ion is a base?
Yes, sir.
Okay, great. Well, we're going to meet some very strange bases and acids now because we're going to get some things that are acids and bases. They don't look like they're acids and bases. But if you remember the rule, an acid is a proton donor, according to Bronsted-Lowry, a base is a proton acceptor. Now, when you draw this line, and you will see questions like this many times, we say that we have acid-base pairs, acid-base pairs, acid-base pairs. Now, what do the acid-base pairs differ by? Come on, this is like a real tough question. Who can tell me what the acid-base pairs? They like, one's an evil twin and one's a sort of a normal guy. But they're very similar. In what way are they very similar, and in what way do these evil the two twins differ? How does that differ from that? How does that differ from that? What has the evil twin got that the other twin hasn't got?
A hydrogen, sir.
Well done. Or to be totally specific, an extra proton, a hydrogen ion. And now, folks, when they ask you, and we go through that paper 2, and they're going to ask you for the acid-base pairs, how will you know that that is not a cousin of that? How will you know not to try and link? How will you know that that cannot link with that? Because do they look different by one proton? No, they look completely different. They come from different mothers and fathers and different families. That's got no chlorine. That's got, if you add a hydrogen to that, it doesn't look anything like that. But if you add a hydrogen to that, it looks a lot like that. So now you're going to have to get used to recognizing acid-base pairs. Okay, that's Bronsted-Lowry, acid-base pairs. Now, I think while I've got this here on the board, what do these two arrows represent? What do the two arrows represent? That the reaction is begins with an R.
Reversible.
Fantastic.
That was Aiden.
Okay, we're back. Now, if it's reversible, is it possible that the forward reaction can be very big and the reverse reaction very small? Is that possible?
Yes.
Possible?
Yes, sir.
Okay. Now, would anyone like to tell me what kind of acid we say it is when the forward reaction is like a giant big arrow and the reverse arrow is tiny? Anyone know what kind of acid we say that is?
It's a strong acid.
Gee, as I say, you guys overwhelm me every time. So this is what we call a strong acid. Not a concentrated acid. A strong acid is one where the forward reaction goes almost completely only to the right. We get very little back reaction formed. Okay, wonderful. So that's called a strong acid. Now let's give you another acid. This H2, I'm dyslexic today, CO3, plus water goes to form H3O plus CO3, 2 minus. Is that okay? Let's have a look. Who can find the acid-base pair of this one?
Oh, which one, sir?
Of this carbonic acid. What on this side looks similar to this? That or that? That. The CO3. So there's your acid-base pairs. In this case, it donates 2 hydrogens. So it differs from this by 2 hydrogens. And then does this look like this? There's your other acid-base pair. Okay, so is that the acid and that the base, or is that the base and that the acid? Let's say, which is this?
That's the acid.
Okay, that's the acid, so this must be the base. Now, of these two, which is the acid? Which has got the most protons to give? Which of these is going to give away protons? That one or that one?
The one on the right, sir.
The one on the right. So this is your acid. This is your conjugate base. Now we say that if an acid can give off 2 protons, we call it, anyone know the name? 2 protons. Got any ideas? No? Okay, the Latin for 2 is, or the Greek for 2 is? Diprotic. Okay, 2 protons, diprotic acid. We get diprotic acids, we get polyprotic acids, we get triprotic acids. Now, do you think that if something can give off 2 hydrogens, it's going to be a very strong acid? Woo! Do you think it's going to be strong?
Yes.
You would think so. But because it gives them off very reluctantly, the forward reaction is a tiny little arrow. The reverse reaction is a huge arrow. And so that is what we call a weak acid. It's a weak acid. Why? Because the reverse reaction is much bigger than the forward reaction. Okay, so that is what we call a weak acid. It doesn't matter if it's diprotic, polyprotic, it's got lots of protons to give. It doesn't want to give them. This partnership hardly wants to fall apart. This is carbonic acid. Carbonic acid, they're a couple, but they're not that keen to fall apart in water. They will, 1 or 2 of them will fall apart, but not many. Does anyone know where we find carbonic acid? Anyone know where we find carbonic acid? Okay, let me show you. I'm just going to go to present. We've got this little and you can tell me in these things whether sorry, which one do I want? No, that one. Oh, this is the one. Okay. Can you guys all see that? Everyone see this?
Yes, sir.
Great. Okay. Let's take a soda.
It's still loading, sir.
Oh, it's still loading.
Okay, we can see it now.
I thought this was soda, but it's a soda pop. Oh yeah, pop soda. That's what the Americans call cool drink. You see it's got a pH of 2.5. So that's a weak acid. And we find carbonic acid in soda pop. Or what we call Coke or Diet Cola or what do they call all those, Sprite and all those things. Okay, so you see an acid's got a pH of 2.5, but it's not really, it's not 1. Okay, let's look for strong and weak things. What do you think? Would orange juice be a strong or a weak acid?
Weak acid.
Okay, let's hit orange juice. Weak, even weaker than soda pop. But it's got citric acid and acetic acid, citric acid and ascorbic acid or vitamin C in it. Okay, what do you think vomit would be? A strong or a weak acid? Or would you think it'd be a base?
A strong acid.
Okay, because we don't often have vomit in the lab, let's try vomit. Look at that, it's quite strong. Because it's got hydrochloric acid, and hydrochloric acid is a strong acid. Okay, what are these? What do you think battery acid would be?
Strong.
A strong acid. Tell me, would it go with the arrow, would the forward reaction be big or small for battery acid?
It will be big.
Look at that, a pH of 1. You don't get much stronger than that. So that's the acid in your car, battery. That's a strong acid. It means the equilibrium is strongly to the right. Okay, what do you guys think of drain cleaner or the stuff we use to make soap? Remember when we made soap, we used drain cleaner. What do you think it's going to be, its pH? Is it going to be acid or base?
Base.
Okay, have a look at that. Strong base. Let's see if we can hand soap. Remember, we use drain cleaner to make soap. So the soap, obviously, you don't want it to be as strong as your drain cleaner. Look, it's got a pH of 10, and that's what kills the coronavirus. Plus the fact that it dissolves the coronavirus. But that strongish high pH makes it quite a good disinfectant. And then anyone know what blood would be? Would it be acid or base?
Base.
Let's try it. Yeah, slightly base. 7.4 is slightly basic. And spit?
It's going to be a base.
Okay, spit is also 7.4. So all the sweets you eat turn into a weak acid, and then the spit neutralizes it. Here's one that surprised me. Milk. I was surprised to see milk is slightly acidic. I thought you drank milk if you wanted to get rid of acid indigestion. And then coffee was slightly acidic too. And what do you think water's going to be?
Neutral.
Neutral or pH? 7. Okay, so let's just go back here. So, now we come to what is a base. So according to Bronsted-Lowry, what is a base? What is a base according to Bronsted-Lowry? It's a proton acceptor. Fantastic. Now there's a second scientist who gives the more normal definition of a base. And this is what Arrhenius says. He says that when you put a base into water, it is a substance that ionizes in water to produce the hydroxide or OH minus ions. Okay, so according to Arrhenius, a base is only this. Anything with hydroxide in it is a base. So if that combines with water, it's going to form Na plus OH minus in water. So the water doesn't really come into it that much. Na plus and OH minus. All happy? So according to Arrhenius, if it's got OH in it or the hydroxide ion, then it's a base. Now, did you guys see the news from Lebanon? Anyone here not know what happened in Lebanon?
It was an ammonium nitrate explosion.
Yeah, there was one big giant explosion. Anyone know what it was that exploded?
So it just says
Anyone know what exploded?
it was ammonium nitrate.
Ammonium nitrate. Matthew, ask them where they've seen ammonium nitrate, in which section of the syllabus.
Fertilizers.
Well done. In fertilizers. So that fertilizer, this was fertilizer they were storing. There's nothing wrong with storing fertilizer, but just don't store it next to fireworks, because fertilizers are also explosives under the right circumstances. So apparently they were storing 2,000 tons of the stuff, or 3,000 next to fireworks. The fireworks went off. Apparently someone might have been welding there. They confiscated it from a Ukrainian ship 6 years ago. You know what it's like? It's like having a garage full of petrol and benzene and paraffin and thinners and everything else. And there's nothing wrong with that. It's just that it could blow up. It could catch fire. So store it away from other people. So when you go home, take all those flammable chemicals out of your house and then put them in the shed at the bottom with the dog at night. And then if it all goes up, you only lose your puppy. Okay, so that's the moral of the story. Don't store it near people. Okay, now we make it from an acid and a base. Now, why is NH3 a base? This is to show you, according to Arrhenius, why NH3 is a base. NH3 is ammonia plus water, goes to form NH4 plus OH minus. So what is produced when you take ammonia and dissolve it in water? You get the hydroxide ion. And that is why this is, according to Arrhenius, ammonia can become is actually a base. Okay. Now, who can tell me which is the conjugate acid-base pairs here, according to Bronsted-Lowry? This must go with which of these two? That must go with the ammonium ion or the hydroxyl ion?
The ammonium ion.
The ammonium ion. And then obviously these go together. Now, Matthew, ask them which of these two is an acid? And how do we know that which one is the acid? Is the ammonium ion or ammonia? Is the ammonium ion? Or ammonia? Which is the acid? What's the rule? Look for the one with more hydrogens. Which one's got more hydrogens? The right or the left?
The right.
3 as opposed to 4. So this is your acid. This is your conjugate base. Of these two, which is the acid? Water or the hydroxide ion?
The water.
The water's the acid, and this is its conjugate base. So ammonia is an acid, is a base by both definitions. It is a proton acceptor. It accepts a proton, and it is also an OH minus producer. And there we go. So now you know the different types of acids and bases. Right. Now, what was I going to do next? Let me think. While I have a sip of tea, what am I going to do next? Okay. Again, what would be a strong base and what would be a weak base? If I tell you that this goes far to the right, is ammonia a weak or a strong base? Weak or strong? It goes far to the right.
It's a strong base.
It is a strong base. Well done. Okay. Now, there is another thing that you need to know, and I just want to present it and show it to you. It's going to look a little bit complicated, but I just want to tell you the difference between a strong base and a strong acid and a weak and a dilute base. There's a difference between a strong one and a dilute one. Okay, I hope you can see this. This is what the water molecules look like, little teddy bears. That's what the acids look like. There's the same, but let's have a look what a strong acid looks like. You've got a lot of these do you see these H3O pluses? All these are to me they look red.
It's
still loading.
Okay, it's done, sir.
Do you see these H3O plus hydronium ions? There's lots of them. That would be a strong acid. And look, you see that the arrow goes, there's your hydrogen plus the acid plus water goes to form A minus, or the anion plus H3O plus. So there's your H3O pluses. There's lots of them. Let's have a look at the difference with a weak acid. In a weak acid, the equilibrium is going not so much to the right, it's going equally in both directions. Okay, they show it's equally in both directions. And look, there's far fewer of these little red hydronium ions. Okay, so that's a weak acid. Now let's have a look at a strong base. We expect to find lots of a metal plus the hydroxide. Metal plus hydroxide goes to form the metal positive ion and the hydroxide ion. So look at the number of hydroxide ions we're seeing here. And then a lot of the metal. So, and then that would be a strong base. Look, the arrow is completely to the right. And then a weak base. They give the arrows equally in both directions. And you don't see too many of the hydroxide or blue, little blue molecules here. So that's a weak base. Okay, so then I just want to see this here. Let's just go back to this. I hope you can see it. Maybe it's still loading. And I want to go back to orange juice. Let's have a look at what is a concentrated acid versus there's concentrated orange juice. If we add water, the pH barely changes. Watch. It's still in the 3 point. It barely changes at all. But this is what we call now a dilute acid. It was a weak acid, but now it's a weak dilute acid. Let's let that out. And let's try a strong acid like vomit. Do you think, now that's a fairly strong acid. If we add water, it started as 2. Now it's a dilute strong acid, but its pH has hardly changed. So you can drink as much water as you like. You're not going to change the pH of the stuff in your stomach by much. It's only changed by 0.38. So this is now a weak, strong, it's a dilute strong acid, meaning it's got a lot of water with it. And the thing you've got to remember is that weakness doesn't, I mean, diluting a strong acid, it's still a very strong acid. And diluting a weak acid, diluting doesn't change whether it's a weak or a strong acid. It's just that dilute means it's just got more water added to it. Okay, so there we go. Now, let's go back here. Stop presenting. Let's just think where we're going to go from here next. What else do you need to know? You now know what's the difference between a strong acid, a strong base, a weak acid, a weak base. Okay, let's just quickly do what happens. What are the common reactions of acids and with other substances? Let's do that. This is what I asked my grade 11s to do, was to take an eggshell and to put it into vinegar. And at the end of 2 weeks, this had completely dissolved into that. That's all that's left. Just a bit of slime. Smells still vinegary. Okay, so let's say an acid plus a carbonate goes to form. Anyone know what an acid plus a carbonate goes to form? You knew what an acid plus a base forms. Salt and water. What does an acid plus a carbonate go to form? Any ideas?
Salt, water, and carbon dioxide.
Carbon dioxide and water and a salt. Well done. So vinegar is it's CH3COOH. CH3COO. Then it's joined to an H plus calcium carbonate goes to form that, and a salt. Okay, guys, let's see if you can find out what is the salt that is formed and where is it going to unzip and join to other things. And then try this one. An acid, phosphoric acid plus sodium hydroxide goes to form what salt and water? Then an acid plus metal goes to form what and what? Okay, anyone got the salt here? Any ideas for the salt? How are we doing, Matthew? Have we got any suggestions for what's going to happen here?
No, sir.
Okay, let's talk you a little bit through it. This is going to split. That is called the acetate ion. It's going to split here. The calcium carbonate is going to split there. That's going to swap with that, and that is going to swap with that. They're going to swap partners. Okay, so this is like wife swap. So what are you going to do? You're going to swap the carbonate. Was married to calcium, but now it's going to marry acetate. So here's your salt. Calcium, but it's got a valency of 2. Acetate has only got a valency of 1. CH3COO minus. And there's got to be 2 of them. So it's calcium acetate. Calcium acetate. Why do there have to be 2 acetates? Because calcium has got a valency of 2. Acetate's got a valency of 1. Okay. Any questions there? Just ask them if there's anything there they don't understand.
So Mustafa wants to know what you're asking.
Okay, I'm asking, do you understand why you need 2 of those for the calcium? 2 acetates.
So Mustafa says he doesn't understand.
Okay, ask Mustafa, what is the valency of calcium? It's in group 2.
Mustafa says 2, sir.
That's right. And the acetate ion has got a valency of 1, meaning it's got 1 hook. So how many acetate ions do we need to satisfy calcium?
2.
2. Well done. So that's why it's Ca, open brackets, acetate ion times 2. It's what we call polygamy. One guy, calcium, has got 2 wives or 2 acetates. Ask Mustafa if he understands that.
He understands it, sir.
Okay. Now, if we said that something has got 2 hydrogen, it's diprotic. What do you think phosphoric acid is with 3 hydrogens? We call that?
Triprotic.
Lovely. This is triprotic. That means this acid is 3 times an acid. Now, if it's triprotic, it means it's going to form 3 waters. 3 waters. If it's diprotic, it forms 2 waters. So if it splits, it's going to split there and there. Those hydrogens, we're going to need at least 3 of those. And then what is going to be the salt if we take phosphoric acid and we combine it with sodium hydroxide? What is the salt going to be?
Sodium phosphate.
Lovely. Anyone know how many sodiums I'm going to need to satisfy phosphate? Remember, phosphate has got a valency of 3. Look, it's got 3 hydrogens. It needed 3 to satisfy it. So how many sodiums is it going to need? Sodium's in the same group 1 as hydrogen.
You need 3 sodiums.
Lovely. And you know what we call it when one woman is married to 3 men? We call it not polygamy, polyandry. So the phosphate ion is a polyandrous chemical. So she's got 3 guys. She needs 3 to satisfy her. That is called chemistry. Chemistry between atoms is nothing different from chemistry between humans. Okay. What do I know about both? I've only been married 45 years. In another 100, I might know something. Okay. So here we have a definition of pH. Is the negative log of the hydrogen ion concentration or the hydronium ion concentration. I remember we ended one lesson there. Now, what if I tell you that water has got a H3O plus concentration? Those square brackets mean concentration of 1 times 10 to the minus 7. What if I said to you that water has got a hydronium ion concentration of 1 times 10 to the minus 7? Would you be able to type that into your calculator? Negative log 1 times 10 to the minus 7. And will you get an answer equals to 7? So get your calculator out and give it a go.
The answer is 7, sir.
Okay, how many? Let me just see how many people got 7. Just hands up. How many of you got 7? Brilliant. Okay, if I told you that the pH of a substance is 7, would you be able to go backwards and get the hydrogen ion concentration or hydronium ion concentration? Now, listen carefully to what you must do. You're going to type shift second function log minus or change the sign and then 7. So you're going to now go backwards. So you're going to press on my calculator, it is shift and log. Change the sign on my calculator, it's in brackets minus. And then you're going to type 7. And I get 1 exponential minus 7. Do you get that?
Yes, sir.
Who got that? Just hands up. Okay, fantastic. Okay, let's just try you with this. Okay, let's try you with this. I know it's going to take some time to come up. Just tell me when you can see it. Can you see it?
Not yet, sir.
Not yet?
We can see it now.
You can see it.
Yes, sir.
Okay, guys, this is chicken soup. It's got a pH of 5.8. I want you to tell me what its hydrogen ion concentration is going to be. I want you to go from its pH to its hydrogen ion concentration. If you've got the answer, won't you just put up a hand so that Matthew can see?
Just say is it 1,58 times 10 to the power minus 6?
Genius. Fantastic. How many people got that?
Only 2 people, sir.
Only 2. Okay, let's try another one.
Shift log and then you put the pH, and there must be a minus sign in front of the pH.
Okay, let's see if you can find the hydrogen ion concentration for hand soap. So what are you going to do? You're going to type shift log, change the sign, or minus 10. Shift log minus. I hope we got more than 2 this time.
It's 1 times 10 to the minus 10.
Yay. Okay, how many people got it? Hands up. How many got the answer 1 to the power of minus 10? You. Okay. Now let's see if you can go from 1 to the power of minus 10 and see if you can get back to a pH of 10. So you're going to say negative log of your answer on my calculator. I'm just going to go. Change the sign, log, answer, and I get 10. Did you guys get that?
Yes, you put minus log and then the concentrate.
I don't know if it's minus or change the sign is the same thing. Come here, my darling. Hey. So when I press negative log of the answer, I get 10. Or you must type negative log 1 times 10 to the minus 10. Okay, is this easy enough? Everyone bored? Okay. Now there's another thing called the P.
Third time again. Almost time to go home. Please sanitize your hands. Educators who need to be on duty, please go outside. Thank you.
It's end of days.
Matthew, thanks a million. You were great. I really appreciate it. And thanks for the rest of you participating like that. If you could bring your paper twos next time, we'll go through that. All the acid-base questions. Maybe if you wanted to, you could even make a start on them. Thanks a million, Matthew.